Hello, everyone, and welcome to the first Surface Ventures Mini-Symposium. Great to see so many of you already saying hi in the chat. Be great to see more of you saying hello, and also to see where you're joining us from today. So excellent. My name is Dr. Sam McMaster. I'm the event manager here at Surface Ventures. So we are a non-for-profit organization, and our mission is to provide world-class material science education for academia and industry. Today, it's my pleasure to introduce our speakers for this mini-symposium and to review the agenda for today. Okay, so here's the agenda. So we'll be beginning with our first presentation from Martin in a moment or two. Okay, so we will then, these times as well are in reference to GMT. So there will be some adjustments if you are joining us from another time zone. Okay, I'd also like to say thank you very much to today's partner, Bruker. We will have a presentation from Sandra Bergmann and Roger Posusta of Bruker in the middle of our event. As you can see, we'll also be releasing some poll questions and handouts from Bruker throughout the event. As you go along, please type your questions into the chat and they will be marked for the Q&A sessions. We will address questions for each speaker directly after their talk, and we will allocate approximately 5 to 10 minutes for this, depending on the exact length of time for the speaker's presentation. We're planning to go for just over 2 hours today, and we'll be sharing a link for your attendance certificate later in the event. So without further ado, let's welcome our first speaker to the stage. This is Dr. Martin Dienwiebel of the Karlsruhe Institute of Technology. I will now stop sharing my slides. Martin, would you like to bring your slides up, and I'll leave stage once we're all set. Okay. Okay. Fantastic.
Can see it. Okay.
Yep.
Yeah. Thank you for the invitation to this.
Oh, sorry. Could you? Apologies. I think there's just set up the screen share again, please.
Okay. Didn't work.
Just do that one more time. My bad.
Let's see. So
lovely. There we go. I'll leave stage now.
Yeah, thanks, Sam, and for the introduction, and also to Thomas for the invitation to this mini symposium. My name is Martin Dienwiebel from Karlsruhe Institute of Technology, from the Tribological Center, which is a joint venture between the Fraunhofer Association and the KIT. And I will be talking about a very traditional kind of coating, graphite, which is well known already, but I want to share with you some of new findings on how graphite actually is able to lubricate highly loaded contacts. So this work was done mostly by my PhD student, Karina, who has finished her PhD already, and Antonia, who worked together with her. It was a larger project funded by the Deutsche Forschungsgemeinschaft, the German Research Foundation, and in our team, we had also partners from the Institute for Product Development, Arndt Jörger and Albert Albers, and simulations were done by Andreas Clemens and Michael Mosler at the Fraunhofer IWM in Freiburg, Germany. Yeah, so I want to talk about solid lubricants, and in particular, graphite in this case. When do you use them? Usually, classical solid lubricants are used when you cannot use a liquid lubricant like an oil or a grease bear. And for example, here in such a ball bearing, you have usually very high contact pressures, which are higher than 1 GPa. And the question in our project was, can you use classical solid lubricants at these high contact pressures that you have here in the context of a ball bearing, for example, or in a gearbox. Another question which we are still looking into is if we can achieve a high service life of such a solid lubricant coating without relubrications, and we wanted to know if they form also a tribomaterial. There are a number of classical solid lubricants that are well known. MOS2 is well known, PTFE, graphite, and several others. But I will be talking today about maybe the most classical one, which is graphite. So graphite is mainly is basically the oldest solid lubricant that we know, and the idea why, or the concept of why it's a good solid lubricant, goes back already to Bragg and his textbook of crystal analysis, and he found by doing scattering experiments that you have the well-known structure of graphite, where you have carbon sheets, graphene sheets nowadays called, which have a close atomic distance, and you have in between the sheets you have a large separation. And because of this large separation, the idea was that you can slide these layers nicely on top of each other, because you have only van der Waals interaction, which is weak, and therefore you can slide these layers freely over another. And this concept, the deck of cards model, or the lattice shear model, is found in many textbooks and still being used nowadays to explain why solid lubricants are working well and have low friction. First doubts came up already in the 1940s, when it was found that basically graphite works well in the lab, but when you bring it up to high altitudes, suddenly you have high friction and high wear, and that is because the humidity is very low at high altitudes, and it was found first in engines of airplanes that when they fly at very high altitudes, that you have severe wear problems. So the friction and the wear properties seem to depend on the environment, and it was found that graphite doesn't work well in dry or in vacuum conditions. Savage did more experiments into this, and you can see here the wear rate of graphite as a function of the water vapor pressure, and this confirms what was found in the airplane engines, that if you have very dry contacts, the wear rate is going up. And also if you use other liquids except water, for example, alcohols or other liquids, you find that it depends, basically the friction coefficient depends on the humidity or the amount of liquid on the contact. And the first idea why this is the case was, or the claim that was made, that these gases and liquids can intercalate in between the layers of graphite, and that increases the distance between the layers even further, and that's why you maybe get lower friction when you have high humidity. Well, this idea has been shown to be not correct quite recently by synchrotron XRD measurements, where it was found that the interatomic distance between graphite layers is actually not changing if you have water or air in between the layers. So you keep the same distance, and in this paper it's also said that this refutes the hypothesis that the low friction of graphite is due to intercalation. So basically the intercalation model seems to be not correct. So the question is, what can be the correct reason for why graphite is a good solid lubricant at high humidity? So we have now several models which we find. So we have the classical deck of cards model, where you have basically just the lattice shear between the layers. The intercalation model, which I've just shown already, that's not correct. And then in other earlier papers, there was also a so-called adsorption model mentioned, where it was said that basically you just need to passivate dangling bonds or surface area with water and passivate defects. And that has been actually also established under low loads. So we wanted to know in our work which model is actually valid now, which model is valid in a technical application and also on a technical surface under high loads. So for doing that, we started to do microturbometer experiments. We prepared surfaces by spray coating with an airbrush. So we had iron substrates, which we coated with a graphite suspension. Graphite was here dissolved in acetone, ethanol, butyl acetate, and methanol, and we just sprayed it on with the airbrush and let it dry, and then did microturbometer experiments where we used, in the first place, a small steel sphere, which was running in reciprocating motion against the graphite surface. We had here a track of 1 millimeter, a normal force of 402 millinewtons, which is equal to 1 GPa contact pressure. And then we controlled the atmosphere in a small chamber using humidified pressured air, which was dry initially. Doing that, we first looked also at the basically at the effect of the layer thickness. And what we found is that basically, you can see here, this is the friction coefficient of the uncoated iron substrate, which is around 0.5. If we coat it with a thin layer, we have, of course, a reduction of the friction coefficient. And if we increase the layer thickness, the friction goes slightly up. But if we look at the lifetime of that substrate, that of course depends on the thickness. So if we have a thicker coating, the lifetime is longer. And the lifetime also depends on the roughness of the substrate. So if we use a very smooth surface, polished surface as a substrate, we have a low lifetime. If we use a slightly rougher substrate, then the lifetime is increased strongly. In the next step, we tested basically the humidity dependence. So we tried to repeat what has been done already in literature. So we looked at the friction as a function of humidity, going here from dry conditions, so as dry as possible. So we can measure only humidity levels below 5%. And we went up to 30%, where we got stable friction over 500 cycles. And what we see is indeed that the friction decreases with increasing the humidity. Above 30% relative humidity, that's the lower panel here, the friction is still low, but we strongly decrease the lifetime. We found out later on in our work that this is basically an effect where we already wash away the coating by excess water that is forming in the contact. And when we plot all the friction coefficients as a function of the humidity, we get something very similar to what has been found in literature already. So we have low friction, so at high humidities, and if we decrease the humidity, friction goes up, and we reach basically high friction when we are here at 5% relative humidity. If we plot that against literature values that we have found, this would fit to our data and show that basically low humidity leads to high friction and low lifetime. Now, next step was to find out what is the mechanism for this um, dependence on the humidity. So we looked at our sliding tracks. What you can see here from top to bottom is the sliding tracks at different relative humidities, which you can see in the top corner. 5% relative humidity and low contact pressure. Here's 5% relative humidity at high contact pressure. And then here, high relative humidity at high contact pressure. And basically, I won't talk about the lower panel here because that was where we washed away the coating immediately. And what you see is that we have metal-metal friction and abrasive wear. But interestingly, what you see here in the case where we have high contact pressures and, for example, here, relatively high humidity, that there is a very thin carbon layer in the contact that remains there. It's almost transparent, but you can see it. It stays in the center of the track and seems to be very thin. On the counter face, this was the steel sphere. We also see transfer to the counter face. So we wipe away some of the coating, but we also have a thin carbon contact spot in the center where we slide against the iron plate. We prepared cross sections from these wear tracks using focused ion beam analysis and prepared then cross sections which we further investigated at higher resolution in a transmission electron microscope. And here you can see these cross sections from left to right. You can see the unworn case, 50 megapascal contact pressure and 1 GPa. And going down here in this graph, we have increased the magnification. In the unworn case, you can see there are graphite bundles which are not well oriented on the surface, loosely stacked, so there are some voids left, some pores, and they don't have a nice orientation yet because they are just sprayed onto the surface. If we look at higher resolution, we can start to see the typical graphite layers and graphene bundles in the coating. What we also see is that we see sometimes graphene bundles which show these loops. So basically, the layers are folded around themselves and form these loop-like structures. And these you can find quite often in the coating. When we go to higher contact pressures after a sliding experiment, what we see towards the surface is that there is not really these graphene bundles are not visible anymore. Instead, we see something which looks very disordered at the surface. And if we go closer to the substrate, then we can find our graphene bundles again. However, at 1 GPa, at high contact pressure, basically the whole coating is strongly compressed and is very disordered in the coating. And this goes down to the substrate, and even at the substrate, we see a thin layer of iron carbide which has been formed there. So looking at the high magnification images a bit closer, you can see here in the unworn case the nice layering of graphite. And if you look at the same coating at 1 GPa, 24% relative humidity, you can see that this is basically not visible anymore. There are not these graphene layers are not visible, and instead we see a disordered structure, and this is basically so-called turbostratic carbon that we see here. So it's a disordered structure of carbon, which has been seen in other cases. For example, in soot, you can find that. So these are graphene layers which are very short and very small in size, and they are not oriented anymore in a parallel fashion, but they are stacked and randomly and form this disordered structure. So we find that the amount of turbostratic carbon depends apparently on the humidity and on the contact pressure. To quantify this a bit further is we performed EELS measurement, electron energy loss spectroscopy, where you can quantify the amount of sp2 bonding in the carbon layer. And we did this here in several windows throughout the coating. In the unwound case, basically the whole coating is high of sp2, and that's no surprise because it's pure graphite, nicely oriented or nicely layered still. But when we look at the same layers after a tribological experiment, we find that there is a gradient in the sp2 concentration. So going from the substrate up to the surface, we can see here at 50 megapascal that the sp2 ratio is decreasing from something around 96% to only 73%. So this shows that the amount of sp2 is decreased, and basically the disorder in the graphite is increasing. And if you look at the 1 GPa wear track, then we find that basically we have values of just around 70 to 77% all through the coating. So depending on the contact pressure, the thickness of the turbostratic layer is increasing, and it's also a function of the humidity. So basically, it seems that the frictional properties depend on the amount of turbostratic carbon that is formed in the layer. To understand the formation of turbostratic carbon, colleagues in Freiburg, Andreas Clemens and Michael Moseler, performed atomistic simulations. So they performed molecular dynamic simulations, and they simulated graphite sliding against graphite because we have transfer of graphite in the first place. And they put water molecules in between. So this was done with tight binding simulations. These were the simulation conditions. The speed was a bit higher than in the microturbometer, but the contact pressure was about the same as in our experiments. The first thing that Andreas tried out is to look at different orientations of graphite in the sliding simulation. So first parallel layers, basically the deck of cards model, then vertical contacting graphite layers. Then he simulated these bundles, and then he also looked at passivated structures. What was found is basically that this parallel orientation is very boring. You have almost zero friction. Also in this case, C and G, you don't see a lot. But when you have these bundles, then you can find that there is basically first cold welding, and then you find that there is a formation of aromatic structures. And you can see that here in the simulation. You first see that there is cold welding between the two surfaces, and then these aromatic rings form, and then the friction drops and you reach low friction conditions. So when Andreas did quite many simulations, and he found basically 4 different cases. One was cold welding, where you had very high friction. The second case was this aromatization, which I've shown you in the video. Then there was a case where you had aromatization with a very few bonds, and the last case is where you basically form a water film on the surface, and then you have low friction.
Apologies for interrupting, Martin. I'm just letting you know you're getting very close to time. So if you could wrap up in about a minute. Thank you.
Almost finished, yeah. And if you look to these cases as a function of contact pressure, you see that basically you transition, or it depends on the humidity and it depends on the contact pressure. You can see here the friction as a function of contact pressures and water density, and you can see that you always have a transition from high friction to low friction when you increase the water density, and the point where you have this transition depends on the contact pressure. You can put this all into fit function, and then you can use this for larger simulation models. So yeah, this brings me to the end. So we have looked at the humidity dependence. We have found that basically the humidity dependence can be explained by basically the amount of water and the formation of this turbostratic carbon layer in the contact between two graphite surfaces. And the formation of turbostratic carbon needs a critical amount of water. Otherwise, you have cold welding, and this critical water amount increases with the load, which also explained the contact pressure dependence. We also find basically that this contradicts the classical model, the deck of cards model, and we have to basically extend the model of how solid lubricants work, at least graphite works, by this formation of turbostratic carbon. Yeah, and with this, I like to thank you for your attention. And if you want to read further, we have this published in 2 papers. Thanks a lot.
Thank you very much, Martin. Fascinating presentation. We just have time for, I think, a couple of quick questions. First one from Alex here, who asks, what was the loading when measuring the coefficient of friction?
Well, yeah, so we varied the load, and we had basically what I'm showing here was 2 cases, 50 megapascal and 1 GPa in these experiments.
Mm-hmm. Okay, thank you. And move on to another question from Timea, I hope I'm pronouncing that correctly, who asks, how do you explain the longer lifetime at higher surface roughness or the thinner coating thickness on slide 10?
Yeah, so the higher roughness helps to basically create reservoirs in the valleys of the roughness of the surface. And by this, you can see that maybe here in this picture, by this you have basically graphite still in the valleys, and that helps to keep low friction for a longer period of time.
Okay, thank you. I think in the interest of time, unfortunately, we're going to have to move on, although there are several other questions, and if we had time, I would also like to ask some, but we must move on to our next speaker. So thank you very much, Martin. Brilliant talk.
If you have further questions, you can reach me by email or
Wonderful. Thank you so much. So I'd now like to invite our next speaker on stage, Dr. Justyna Kulczyk-Malecka from Manchester Metropolitan University.
Hello, everyone.
Hello. Okay. Would you like to bring your slides up, Justyna, and then I'll leave stage and let you begin presenting.
Okay, just bear with me a second, and let me know if you can see this slideshow.
Brilliant. I can see it, so I'll let you begin.
There.
Thanks.
Fantastic. Okay, thank you so much, guys. So hello, everyone, and thank you for having me. This is very exciting. Well, the spoiler alert, I'm not a tribologist, so my presentation is going to be slightly different. However, I am an expert in surface engineering, and my background is in general materials, but specifically coatings deposited by magnetron sputtering. And today, I'm going to share with you 2 case studies very ambitious, to case studies. For the time I've got, with the coatings basically deposited to resist corrosion with the different mediums. So the first one is going to be under the umbrella of NNL. So this is the project sponsored by Advanced Fuel Cycle Program. And we've been looking at corrosion resistant coatings from heavy liquid metal coolants in fast reactors. And the second one is going to be a little work on nitride coatings for thermal barrier applications in titanium alloys for aeronautical applications. So I'm going to start with the corrosion resistant coatings in steels for heavy liquid metals. So Advanced Fuel Cycle Program, basically for those of you who doesn't know, this is a program that supports cross-cutting research into fuel cycles for achieving net zero targets within the UK. So it's kind of the addition to the UK's Advanced Molecular Reactor Competition, which basically was the program that in 2 stages down selected 3 technologies that are of interest to achieve those targets. And one of them are actually lead-cooled fast reactors. And you can see basically like a little picture over here of the Alfred, which is a European demonstrator of such reactors. And UK actually has quite a bit of a background, 40 years of operating in the past with the fast reactors. However, with the slightly different coolant as a light liquid metal such as sodium. And, we believe that basically lead-cooled reactors can deliver the sustainable commitment that UK has with, provided that we can actually solve the materials challenges. So why lead as a coolant is attractive? Basically, it has the advantages of a very rapid heat removal in comparison to water, for example. So there is no requirement of highly pressurized vessel systems, which is a bonus. Lead has excellent neutron properties, and it's great radiation shields against gamma rays. So, there are advantages. However, of course, there are always going to be disadvantages if it comes to a coolant that actually is solid up to 327 degrees C. And of course, we can bring down the melting point. However, that normally creates a highly corrosive or more corrosive than a lead itself, a solution of a lead bismuth eutectic. So, it's not really an advantage if we're actually looking at it from the materials point of view, because as you might know, cladding materials must resist chemical corrosion due to, whatever medium is in contact. Oxidative corrosion as well, because they often operated at relatively high temperatures. In this case, we're talking up to 700 degrees C. And of course, those materials need to be resistant to fast neutron irradiation. So there is a lot of issues that need to be solved first. Right, so in this project, we're looking at coatings that has been deposited using magnetron sputtering technique. And you can see over here the schematic of the rig. So this is side elevation when we've got substrate placed on a rotatable substrate holder beneath 2 magnetrons. So we're sputtering down. And for this study, we deposited series of coatings. It's basically a combination of alumina with Ficrol. So either a separate Ficrol or alumina coatings onto stainless steel type 316L, or a combination of both. And then, of course, we expose them at elevated temperatures to a molten lead for many, many hours, and those coatings have been then characterized. So the testing in molten lead was carried out at Enea facilities in Italy. So over here, I just want to basically show you some pictures of how the test was carried out. So I'm not going to go into the details of that, but the important thing is that we actually tested at high and low oxygen concentrations up to 1,000 hours at 500 degrees C. And I'm just going to point out to us received samples over here that are nice and shiny, silvery. This is alumina coating formed on stainless steel. And this is going to become important on the next slides when you actually see how the coatings look like after the corrosion. And very quickly over here, just to kind of show you how the as deposited coatings look like. So basically they conform with the with our steel. Steel hasn't been treated, so basically it's unpolished. So this is the worst case scenario if you kind of consider that for the coating to be deposited on top. We can see a relatively thin aluminum interlayer, and this is basically deposited during setting up for reactive sputtering in the system. And at the bottom, you've got alloys on top of a ficrol. Ficrol, because of course, is quite conformal with our stainless steel. It's very difficult to see it in the under the SEM without any treatment. So let's move on to actually the results on the molten lead. So what you see over here are aluminum coated with aluminum oxide on top, ficrol and ficrol alloys samples, and in each case, obviously, they more darker than the ones that I showed you on the previous slide, which were as deposited. And let's start basically with analyzing whatever happens to alumina coated samples. So the arrows pointing are actually solidified lead on the surface. And of course, we took a closer look into what is happening to our coating. And as you can see, lead has those round structures. They're relatively flat and kind of smeared across the sample, which suggests that actually wettability is relatively high, which is unwanted in this case, but we still can see plenty of coating on the surface. However, we can see those areas where iron is kind of shining through from the substrate. So either those areas are being removed by the lead, or these are relatively large pinholes that, formed pitted corrosion based on the molten lead exposure. So if we actually zoom in into this kind of area over here, we can more clearly see the structure of our aluminum oxide on top, and we can see plenty of cracks that could be intragranular. They can actually, again, be because of the pitting corrosion. And we can see that through those cracks, we actually see iron shining through, coming through. However, elemental analysis shows us that we do still have plenty of protective coating on top. So moving on to our ficrol, the structure is slightly different on the top. So what we see actually are very nice bubbly proper droplets of molten lead existing after the treatment. Overall, the area outside the droplets looks a little bit better. So basically, we've got far less lead that stayed on the surface. However, plenty of erosion or pitting visible on the surface. So if we scan those nice circular area, we can see that like a proper solidified lead droplet has stayed on the surface. So it seems like, both coatings has slightly different wettability towards molten lead, with, ficrol showing definitely less wettability and higher contact angles. So what was the case in case of the double layer? You can see over here that the coating looks relatively dark. However, we don't have such lead spots on the surface. What we can see is this coloration, and image that is relatively zoomed out looks the coating looks relatively uniform. We can see those little spots over here that probably are molten lead, and actually if we zoom in, we do see that those spots that seems to be at the grain boundary, so intragranular, are actually the lead that's solidified on surface. We can also see actually nickel over here, and this is not a great finding because we don't have any nickel in our ficrol coating, so the nickel obviously is kind of coming from the substrate. So those cracks that are generated most likely actually come all the way down to the substrate. But obviously, without knowing if the lead is able to penetrate through them, we cannot comment at this point. So let's see what is happening if we're going to investigate our coating from the cross section. So this is alumina coated stainless steel after treatment. And you can see that, in the larger scale, there's a lot of rumpling going on. However, on the closest spot, if we're going to do EDS analysis across, so you've got line here, line analysis across the coating surface into the substrate, we don't really pick up any lead signal, unless, of course, we do the same scan on the actual droplet. So on the right-hand side, what you see, it's the double layer of ficrol and alumina on top. And again, you can see some rippling, a little bit less perhaps. However, what we see in this coating are those indent-like structures. So clearly we can see that this is probably something that was a pinhole in the coating that under corrosive environment expanded into a crack or a pit that probably would serve as a fast path for the corrosion. So we did TEM on those images as well. So this is basically what you see. This is high angular dark field image, and on the top over here you can see aluminum oxide, and then this is that interdiffusion kind of zone of ficrol being deposited. And if we kind of bring closer those areas over here, we can see certainly that there is a crack that is through and through our aluminum coating. So from the perspective of what could happen is something that we don't want to see. However, doing again EDS analysis across the TEM sample, we don't really see lead kind of coming through the coating. We can see aluminum oxide on top. We can see that interdiffusion zone. We can see some agglomeration of chromium within the ficrol, but we don't really pick up the lead at this point. So, okay, we did the same analysis, of course, for ficrol. And the ficrol looks slightly different. So there is far less rumpling if we look at the across the larger scale. However, we can see a lot of chromium agglomerating within the coating. And from the SEM EDS, we can't really specifically say what is happening here with lead, because we're picking up the signal at the top and at the bottom of the coating, which basically is quite inconclusive. So, of course, what we did was similar to alumina oxide, or oxide coatings, and we did cut lamellas using FIB that has been tested using dark field in TM. So what do we see here? Of course, so we see those agglomerates or chromium-rich areas, but what we couldn't pick up with the SEM EDS is this line of aluminum over here. That is suggesting that actually aluminum is undergoing our inward diffusion, a process that is well known, either from coatings applied in different industries, like thermal barriers for jet engines or gas turbines, or there is plenty of research about diffusional aluminum based coating. So what we see, most likely aluminum from our ficrol coating is depleted and travels towards the interface between our substrate and the coating. That could be related to actually occurrences of those chromium-rich spots or parts of the coatings, which looking at the oxygen image over here, we can actually see that chromium oxidized a little bit in this part. I'm going to stop over here because this is an ongoing project. So we are at the phase 2. And what we see from now, for now at least, of course, our coatings get corroded over 1,000 hours exposure into the molten lead. However, we don't really see much results with lead actually penetrating through the coating. So perhaps those pinholes, those pitting that we see are not going to be that detrimental for lead itself. However, as this is ongoing research, I don't want to make any conclusions regarding that at the minute. So over here, I'm going to move on to my second case study, because obviously we've got limited time. And I'm going to talk a little bit more about actually, this is part of the study that is pretty much completed. A lot of material has been published from our group in this one. And it's quite interesting project as we developed coatings to protect titanium alloys, and we're looking at aero engine applications here. And those, for you who doesn't know, of course, if we talk about combustors and turbines, nickel-based superalloys are majority of parts that are made of that material. However, in modern turbines, where weight obviously is crucial, a third of the structural parts is made of titanium alloys, because of course they've got low density. Titanium alloys have low densities, hence it's beneficial to perhaps replace those parts. However, they obviously cannot resist as high temperatures as perhaps nickel alloys, and the problem is with the brittle oxides that are formed on top of titanium. So it is well known that alloying aluminium into titanium helps with creating better mixture, maybe less or more protective oxides on top of brittle titanium oxide. And a lot of studies actually shown that incorporating a protective or barrier layer of nitride coatings provides excellent protection for titanium alloys. And we actually did very similar things. So we designed our coating that has been tested up to 800 degrees C for 200 hours. And our aim is basically to achieve good oxidation resistance for those alloys. And of course, the advantage is also a wear resistance for applications in compressors or gas turbine engines, if we can make the coating that actually doesn't disintegrate over time significantly. And again, magnetron sputtering was used to deposit those coatings. And in this case, what we've got is bilayer structure. So we deposited those on titanium and pure titanium and titanium alloys. So we've got a molybdenum interlayer, and on top of that is silicon aluminum nitride. So coatings are relatively thin. And in this case, our chamber setup was slightly different. So we had a chamber with 3 magnetrons, 3 targets simultaneously placed with the substrate holder in the middle that was rotating. And we've been sputtering here vertically. This is top view of the cross-section of the sputtering chamber. And then, of course, coatings has been treated post-deposition. So we introduce isothermal oxidation in air at 800 degrees up to 200 hours, and thermocycling for the same time and at the same top temperature. So let's look how our silicon aluminum nitride moly coatings look like. So as deposited coatings is not that interesting, I would say, because it's glassy-like structure. The STEM images over here basically don't show much. If you go into, again, dark field images and zoom in a little bit more, what you see that actually our silicon aluminum nitride is a coating that has silicon nitrides matrix that is amorphous with aluminum nitride dispersed in it. And from the halo in the diffraction pattern over here, we can tell that the coating is amorphous. And just to kind of give you a broader picture how the coating oxidizes, and I'm going to get into more details in a second. Here's the far image of the material with the coating being deposited on top. We don't have any oxide scale visible, and the bare titanium in this case, or titanium alloy over here, visible on the side where the oxide scale is clearly formed. So just based on that is a hint that our coating actually provides quite good oxidative corrosion resistance. So how does it happen basically? How do we manage actually to protect the titanium alloy from that oxidative corrosion? So as you go from left to right and compare how the coating structure looks like, what we can see, the interdiffusion zone grows significantly as we kind of increase the time of the oxidation. So you've got half an hour over here, where we've got some interlayer being created between silicon and moly, and then beneath molybdenum. And that actually interdiffusion, interreaction zone, as we call it, increases as you increase your oxidation time. I'm just going to point out over here that silicon is actually diffusing inwards, and based off having titanium related structures, so we've got a mixture here above the molybdenum. So we've got, as I like to call it, lean titanium nitride mixture with titanium silicide intermetallic compound. That actually...
Hi, Justyna. We're just at about 20 minutes there, so if you could...
Okay, sure. So basically, we did a little reconstruction of what is happening at that interdiffusion zone. We can see that our silicide actually is not continuously distributed beneath. We can see some pores as well. And I'm going to very quickly finish with this one. So what we actually found, that having that discontinuous layer of silicide with lean titanium nitride created underneath silicon, it actually slows down the interdiffusion process. So even though we consumed a lot of silicon aluminum nitride, we don't see titanium progressively traveling forward above silicon aluminum nitride coating, creating the oxide on top. And the last, I'm promising, what we found, the titanium nitride formed underneath actually shows high stacking faults and mechanical twinning, which actually helps with protect coating from delaminating under oxidative corrosion, because of course it can adapt those adaptively deform during thermocycling, reducing cracking and debonding of the coating. So yeah, like I said, it's very ambitious to present this all. So I'm just going to skip through to the summary. And yeah, I just want to thank everybody who has been involved in those two little projects. And yeah, I'm happy to answer any questions if there might be some.
Thank you very much, Justyna. Really great presentation, but yeah.
Yeah, a lot. Very ambitious.
two very different case studies, but we've got two questions, so we'll just go with these and then move on to our next talk. So Girish, I hope I'm pronouncing that correctly, has asked, can you explain how the molten lead test is carried out? Were the samples put in a furnace?
Yeah, so basically, I'm going to just quickly go back to that slide where I can show. Oh, come on. Yeah, that's the one. So as you can see over here, you basically have like a vacuum vessels with a crucible in, yeah? So obviously it's liquid lead, so it has to be heated up, yeah? And what you do, you basically immerse your samples inside. So this is controlled environment, closed with reduced oxygen, yeah, at elevated temperature. So you're making sure that your lead is at temperature, because otherwise it would solidify. And like I said, we didn't carry on the test, so this is facilities in Italy. So so yeah, so they've got the know-how.
Got it. Thank you.
It's part of the industrial collaboration. There are stuff that I shouldn't say probably. So
yeah. No, it's okay. Thanks so much for answering. So we'll do our one final question now from Biplab, who asks, why not directly coat the oxide layers, for example, aluminum oxide or silicon oxide, to achieve high temperature oxidation resistance?
Yeah, so the idea is actually to do it, but basically, as I showed you how our chamber works, we don't have any shutters. So as you basically start the deposition, there is going to be some aluminum that is going to be created first. So the problem with aluminum oxide deposition using magnetron sputtering is the relatively low deposition rate. So what you want to do, sputtering reactively, you want to make sure that you add the optimal conditions between your metal to oxide ratio, if that makes sense. So if I would be in so-called poison mode, it wouldn't be such a high efficiency coating. So it would take extremely long time to deposit the coating, yeah? So that's why. Hence, we can see a thin aluminum layer in between. However, saying this, the picture that I showed actually shows the thickest one that we created. but it's easy to see it then, when you see.
Yeah, just good to know. It's still present there in the structure, despite the, what you're doing operationally to try and minimize it.
Yeah. So that's the idea. Plus, if you're kind of thinking about depositing onto metallic surfaces, sometimes having a layer of metal actually helps with adhesion.
Yeah.
So you want to minimize as well thermal coefficient mismatches between your substrate and your coating.
Yeah, I mean, that's classic metallic interwear that you might find for DLC coatings or gradient layers, depending on exactly where you need the DLC to operate. But yeah, so thank you very much, Justyna. I think with that, we're about time to move on to our next talk. But thank you so much for your presentation. So now,
thank you. I'm going to leave stage now. Thanks.
Okay, thanks so much. Let me invite Sandra Bergmann from Bruker on stage, who will be delivering a presentation on Bruker surface preparation and analysis with white light interferometry. So let me just bring those slides up. There we go.
Thanks a lot. Can you hear me well?
Yes, I can hear you. And just a note for the audience, I think for the Q&A after this talk, Roger Posusta, also from Bruker, will be joining to help answer any questions. But for now, I'll leave stage and let you begin presenting.
Right, thanks a lot. So hello and welcome to our talk about surface preparation and analysis using white light interferometry. My name is Sandra Bergmann. I'm product marketing for optical profilers at Bruker, and together with my colleague Roger Posusta, who is from our application development team, we have prepared a talk about surface preparation and analysis using white light interferometer for you. So surface preparation itself, or surface preparation, is a vital part throughout the industry to guarantee surface functionalities and ensure coatings, adhesives, or other materials applied to the surface to adhere well and provide a durable bond. This is especially critical for the longevity of the finish, and therefore a key factor of the quality. An in-depth analysis is a key factor and delivers crucial knowledge for the development in coatings and surface finish, as well as secures the manufacturing quality of high-precision manufacturing parts. But let's first jump into some definitions. So when it comes to surface preparation, as mentioned in the intro, surface preparation is essential for getting a surface well prepared for coating, paintings, lubrication, adhesion, lining, and appearance. The process of surface preparation is either a mechanical or a chemical one, and is changing, preparing, and or cleaning the surface of already existing coatings, residues, surface imperfections, organic matter, oxidations, and other contaminants. To get reproducible surface preparation, as well, of course, the handling and the storage of the samples are important, but it's also very important to obtain and follow the appropriate written specifications, as well as to check all those procedures along with qualified measurement capabilities. And for that, non-contact white light interferometry measurements can characterize and control these surfaces, even repeatable to national traceable standards. So let's go into the surface finish. Surface finish, or the surface texture, the surface topography, is characterized by three main characteristics, which is roughness, waveness, and the lay of major surface texture, which is nothing else than the direction of major surface features. Roughness and waveness are the two main features. to control and observe friction and to check on surface formation caused by sliding, wear, coating, lubrication retention, and it is also important to qualify the visual experience. Now each manufacturing step produces a different surface texture. So you can now see here on the right side typical machining processes and their corresponding roughness, mean roughness value, the RA, where you can see, for example, for forming, casting, abrasives material or metal cuttings, what kind of roughness is expected. So, but to obtain roughness, the mean roughness value, you measure the surface now more or less along a single trail when it comes to 2D surface texture. When it really comes to an RA measurement, you are measuring along one trace, one profile, with, for example, a stylus measurement tool. From the raw data received, you can then use filter methods. For example, you can use the high frequencies to pass. You can obtain the roughness profiles, or you can also use low pass filters to just let pass the waveness of the profile and then obtain the single parameters. But the RA value, which is a 2D parameter, is only one part of the whole story of the surface. When you want to understand the whole surface, 3D surface texture measurements should come into play, characterizing the roughness and waveness of the whole surface of large areas of the sample. We will also discuss the challenges of only using 2D parameters a little bit later in this presentation. But let's first take a look at some example. For example, how do different machining processes look like and how do the surface and therefore its characteristics vary? Here, for example, we are having a measurement from flat lapping with 0.2 microns. Then here another flat lapping or flat lapped surface with 0.4 microns. The next one is a turning data set with 1.6 microns. Then you can see here horizontal milling with 6.5 microns. Then same flat lapping, this time in grayscale colors, and also vertical turning. So you can already see that different machining processes gives you really completely different surfaces, and therefore they can be quantified by them. Another very interesting or high demanding surface or surface finish are implants, for example, for knee joints, as you can see that here. This example, the surface preparation was done by high energy tumblers. And you can see well the differences of the different textures between here the raw casting, the initial polishing with the media, the high-end media polishing, total different surface already, and if you're then finishing with the final hand buff. Another very interesting application is the surface texture measurement for qualification of pre-paint surface by using 3D spatial frequencies. This special parameter will be also especially talked through later by a presentation by Don Cohen from Michigan Metrology. But you can see here, we can quantify the past and the failed the failed surface, why the painting, for example, afterwards showed an orange peel, and we can determine if it's best to field just by spatial frequencies. Another very interesting part is peening. Peening is a process of introducing stress into material, and that then changes the material properties to improve corrosion or cracking resistance, or to check on fatigue and coating effects. And you can see here the very different surfaces of a shot peen surface, of a laser shock peen surface, and electropolishing surface. And last but not least, 3D metrology can also characterize and provide information about corrosion evaluation. Here you can see an example of corrosion measurements. The corrosion measurement can be even done fully automatically, and you can then gather everything from grain sizes to grain coverages to grain heights, and check on the corrosion itself. When it comes to surface preparation and the preparation for example, for special coatings, your attention should not be only set to the surface itself where the material is applied to or where the coating is applied to. Also, the media used for the surface preparation plays a key role in the surface preparation. So also their quality, the controlling of that can help you far before that to avoid any quality challenges. So therefore, let's take a look into some abrasive materials examples. For example, here you can see 3 different grids of polish material. And you can already see here's a 150 grid, or two. Here are 2 different 150 grid. How different this polish material, this abrasive material already looks like, and of course a 320 grid material. And from that you can also derive with white light interferometry, with 3D optical measurement. You can do automatic analyses, check on the grain distribution, grain heights, grain sizes, how the grain looks like, and then quantify if your abrasive material is well enough. Here I'm having another application. This one is from the semiconductor part, and here you can also see that everything is done automatically, and you can even check on each single grain. Is it good? Is it, for example, chipped, or is it already damaged? And then you can obtain why do you have maybe some patterns in your surface, or what is exactly happening. So, seeing all these applications, with which analysis parameters you can now work with? When it comes to surface texture and its quantifications, the so-called S parameters or areal parameters are the most accurate ones to use. These parameters can be divided into 4 different groups. The amplitude parameters, which are very analog to the 2D parameters and derived via the height data and the form. Then the spatial parameters, which are derived from an autocorrelation functions and are here to help you to find out the preferred direction of a surface, as well as the functional parameters, which are directly derived from the Abbott curve or the material curve, with which you can access, for example, lubrication behavior or adhesion behavior. And then last but not least, of course, we're having here hybrid parameters, which are a combination between height and spatial parameters. On the right side here, you can also see for your different functions what you want to invest. You can definitely see what kind of parameters are having the most evidence for you to invest on. When we take a look a little bit below on, for example, bonding and adhesion, you see that amplitude and functional parameters are the one with the most evidence. This is also valid for painting and plating. And to this functional, they are derived from the so-called Abbott curve or the areal material ratio curve. This one is a direct function of the surface texture profile, and with this areal material curve, it gives you a very, very wholesome overview about the information about the core material of a surface, as well as the core roughness, and also all the valleys and depths. Gives you a very nice overview of that, and with this you're having you can really determine a lot of functional informations about your surface itself. Another very interesting and great application itself is the film measurement. So with this film measurement, you can measure film thicknesses from nanometer to micrometer films, and we are obtaining that with our white light by measuring the film surface, then measuring the film substrate interface, and then getting out of that the film thickness. But now we have talked a lot about the applications. We have talked a lot about what kind of applications, what kind of analysis we can use. But how does white light interferometry works? So here on the left side, you can see the basic components of a white light interferometer. From a light source, in our case, it's a white or a green LED. We introduce light into an optical bath. This light got splitted into a reference beam and into a beam for the measurement itself, which get directed to the sample. Both light beams are then combined together at the beam splitter and focused onto a camera, where it then comes to an interference pattern. And from this interference pattern, we translate it into peaks and heights and get therefore the whole 3D surface. So this technique is very accurate. And with the next slide, we want to show you how accurate it is, and that we can really translate different roughness comparator standards, which we have measured with our white light interferometers, and how good they correlate. You can see here on the left side that we can use the whole measurement settings and the whole settings that needs to be checked on those roughness comparator standards, and also you have to have a certain sampling length. And here below you can see the direct correlation for our 3D optical profilers, and in green the independent certification, and you can see how well it correlates. Why does white light correlate in that case so well in somehow comparison to some for example stylus filtering or stylus parts? When it comes to stylus measurements, you do already a lot of filtering and using cutoffs, deciding on which kind of stylus you're using, on which kind of shape and style of stylus you're using. You can see it here, for example. This is a good example to show how the surface itself looks like in violet. And when you're using different styluses, for example, a 5-micron stylus or a 10-micron radius stylus, you're getting a total different impression of of your surface, you're getting a different impression of your roughness values, but also on how many peaks and how deep they are. And here, also optical metrology plays a good role, or gives you a good opportunity to avoid this kind of filtering. Of course, when using different objectives, you're also having different lateral resolutions, and this lateral resolution is not in total, but you can translate it somehow to the size and the shape of the optical of a stylus itself. You can check on the lateral resolution, and of course you can measure with a 5x objective here and the lateral resolution of 2.2 micrometers. We're having here a test track with a pitch of 10 microns. But with optical profilers, you can also use a different objective with the same height resolution, with the same set resolution, but having a lateral resolution of 0.7 microns, where you have absolutely different information and getting more into the right details of the surface itself. You can go even up to, for example, 50 microns, where you're having a lateral resolution of 0.5 microns for a pitch measurement of 10 microns, which is for sure more accurate than with anything with any stylus measurement itself. But how many or what kind of magnifications are available? The magnification when it comes to white light is is only important when it comes, like here, like on the last slide, to the lateral resolution.
Okay, last slide, Sandra.
Last slide,
okay,
or
got
almost.
It.
Yes,
Right.
thanks. Yeah. So we're having here we can offer different kind of objectives. All these objectives can have a different lateral resolution up to the 115x objective, but which is very important and comes to other techniques and is different than other techniques than white light interferometry. We're always having the best set height resolution, and therefore we can always offer the right information about our set heights. So I will now just sum it up. So white light interferometry itself is universal for all application. We are having the same height accuracy and set for all magnifications. We can offer fast measurements over large areas, access also different areas for vertical bores with specialized optics, are able to measure all kind of materials from shiny to curved and colored. Transparent finish or thickness measurement is also one part of it, and which is very important, is a non-contact technique, and there is no damage from the surface itself, like from a stylus. So, coming to an end, thanks a lot, and yeah, happy to hear some questions.
Thank you very much, Sandra. So let's invite Roger on stage as well to help with this. We've got 3 questions. So in the interest of time, we'll take these questions. However, as I said before, if the audience does have any additional questions, please do type them into the chat. You can address them to the speaker that you would like to answer them. Okay, and they can get back to you. Okay, so we'll begin with a question from Yochin, possibly. Apologies if I mispronounced that, but they ask, how long does such a typical 3D measurement take on a 1 centimeter squared area?
Oh, that's a very good question. It all depends on, of course, the magnification we're using and the measurement mode. For very smooth surfaces, mirror types, we use what we call as a phase shifting mode, which autofocuses and takes a measurement within 5 seconds. For more vertical modes, then it takes slightly longer, and it all depends on the height. And if we didn't get into, for larger XY areas, we do stitch multiple images together for that analysis.
Okay, got it. Thanks, Roger. So move on to the next question now from Jakob, who asks, what is the thickness of transparent film that can be measured with white light interferometry, and what is the precision of the measurement?
I knew that question was coming. It's always a dependence on the index of refraction of the material. We can measure over, well, from nanometers all the way up to hundreds of microns, but we have to be able to get the light through the material. So if it's, definitely slight transparent, we use a lower magnification, the light's more vertical, and we're able to penetrate from the top to the bottom of the surface. But definitely it's sample dependent.
Okay. Got it, thank you. Is there any change in the precision of the measurement versus what was shown in the slides for transparent samples? Just the second part of the question asks, what's the precision?
Oh, I'm sorry. It's like, again, it all depends on the material and the roughness. But no, it all depends what mode we have to use in magnification.
Sure.
But yeah, typically we like to get a sample and test it and tell you exactly on your sample what the feasibility is.
Yeah, of course, transparent samples are quite awkward. It's very much a case-by-case basis. Okay, so let's move to the last question that we'll answer here from Giselle. Can transparent film roughness be measured when it is deposited onto a cylindrical sample? For example, small radius, 5 to 10 millimeters in diameter, or perhaps large areas such as 4.5 by 2 millimeter areas?
Typically, yes, we definitely can do it. The trade-off with optical or any measurement system is getting the sidewalls are down. And I think you sent out the NP Flex brochure where we have a rotary stage where we can rotate the sample. And that way we're always on the apex of the sample and we're getting the best light return on it. And we're able to go around the sample and measure that way versus trying to get light back from a sidewall where it's bouncing in the wrong direction, if that makes sense.
Yep, thank you. Okay, so we have two other questions, but I think in the interest of time, we'd like to move on to the next speaker. Roger and Sandra, are you able to address those answers to the registrants in the chat, please? And we'll move on to the next speaker.
Thank you, yes.
Okay, perfect. Thank you so much. So now we'll be moving on to our next speaker, Dr. Michael Burkinshaw from Cummins Aircraft Components. Yeah, sorry, Donald, not yet. You'll be next after Michael. So I'll just invite Michael on stage. Okay. There we go. Okay, lovely. Michael, I think there's just a slight, you could adjust your mic position slightly. We can hear you breathing.
Great. Okay. Hopefully that's a bit better, Simon. I'll talk through it, and then if it's particularly annoying, please let me know, and I will move it again.
That's perfect now. Thank you.
Fab. Okay. I need to breathe, so hopefully that's going to help. Okay, right then, everyone. So I'm going to talk to you a little bit about experiences, insights, and future challenges that we've had within Cummins Engine Components regarding tribological coatings and surfaces. So in terms of how we do tribology at Cummins, I thought it'd probably be good to start off with that to begin with and then lead from it. If you think about a very simple chart here, so we've got confidence and capability on the y-axis and then method simplicity on the x. What we try and do is we have various different levels of techniques, methods, analysis processes based on technical readiness level. And that's split up on the x-axis, so you can see them at the moment. And what we try and do is we relate each box to the next one through correlation. So typically what we do is we start from the right-hand side, where we've got the analysis-led design piece, where we're modeling the interface. We're doing a lot of the analysis to understand the contact conditions and then the evaluation of the tribological risk. And from there, we then do some work from a pure material selection perspective. So we're looking at reviewing the Trabo system. We're doing consultation for our internal project teams and then our research projects. So we generally feed one of those boxes off against the other and make sure that we've got that correlation in terms of we've got the right material properties in the model, etc., etc. Once we've got that information, we're happy with it, we'll then take it to the next level in terms of the technology readiness approach, and we'll do our material evaluation. And that might be analyzing the microstructure. We might have a look at the chemistry, or we might do some mechanical property analysis, be it macro, micro, or nano. And from there, once we're happy with the simulated interface, once we're happy with what we're going to actually be testing, we then go forward to doing the tribological test itself. And that could be something very simple. I mean, it could be a very idealized interface, like a pin on disc, pin on plate, ball on plate, whatever, in a tribometer. And then leading on from Bruker's presentation previously, we may use something like an interferometer to then analyze those surfaces to understand how much damage have we caused, looking at the surface topography, the worn volume, etc., etc. We will then feed that information all the way back to our simulation model and make sure that, again, we're correlated in terms of the wear rate, the wear depth. And if we are, and we're happy with everything, we'll move forward to doing component level testing. We'll do that on a test rig and using much more complicated systems. And again, once we finish that, we'll go on to product-based testing and then finally the system-based test. Obviously, the further we go towards a system-based test, the more it costs. So we really need to be able to fail effectively and determine what works and what doesn't work. So we do this quite robustly, but there is an element of working with Agile as we're working through this process. Okay. So I want to give you a bit of experience of things that we've seen in the past, and just to bring it home to stuff that we make within our business and we sell to our customers and you use in a heavy duty truck, for example. These are two systems that we have within a modern turbo machine that we find within a heavy duty truck engine, where we have either a variable geometry system or a wastegate shaft and bush. Both have similar type purposes. The variable geometry system, I'll go through that in a few more slides, is really there to provide us with lots of different geometries of a turbine stage. So we can close the gap between the orange shroud and the green nozzle to allow us to effectively have multiple turbochargers in one. And so we've got lots of different tribological interfaces there. We've got the orange against the silver. We've got the green against something that's not shown there, a seal ring. We've got various other things that are in there that we need to be able to monitor. And we've got very arduous operating conditions. So this is operating up to 800 degrees centigrade in different exhausts as well. So we've got different chemistries of exhaust with different temperatures. The same is true with the wastegate. And there we've got the shaft moving relative to the bush. And we've got the valve obviously then hitting its seat inside the housing. So in terms of some effects here, to show you the effect of different things of surface treatment, This is an example of a real-world case of what we do. Here, this is showing you from stainless steel against a stainless steel. So we're doing a pin-on-plate, unlubricated test. And we're doing this at various different test temperatures. This one is just showing you the baseline. So this is showing you if we've got an untreated pin and untreated plate, we have a certain amount of damage on those after the end of this test. And you can see it's quite we don't want this type of behavior. That's what we don't want. We don't want this type of behavior on our interface. So what we try and do is minimize the amount of wear. We want to optimize the wear rate. And so what we're doing here is we're introducing a surface treatment onto the plate itself, just the plate. And you can see already that's had a significant effect on the total volume of wear, the total damage that we've seen in the interface, but we've still got quite a bit of damage on that pin. So if we then treat both the pin and the plate, exactly the same test conditions, you can see we very much reduce the amount of wear. And the question I would always ask my team and the customers that we have, both internal and external within our business, is how good is good enough? You know, we don't need to engineer something that's going to last forever, but we do need to engineer something that will last for the appropriate life of time. So that might be the final solution. Indeed, it might be the first solution we see here, but we need to work that through. And what does that mean in reality? Well, when we look at the treated component versus its untreated counterpart, you can see the untreated component, you've got large volumes of abrasive wear. Whereas if we look at the surface treated component, again, we've got that abrasive wear, which is what we want. You know, we don't want to promote adhesion, galling, but we've significantly reduced the wear volume. So we've increased the life of this component, and therefore this means that we can use this component much more reliably, much more robustly in service. Another effect that we see is the effect of the temperature and the surface treatment. So here, just to give you an example, is the effect of that temperature as we're changing the different condition of that surface. So you can see that we've got a stainless steel pair, for example, and then a coated pair, and then a cobalt-based superalloy pair. And you can see the influence of the surface treatment is quite significant compared to the base stainless steel. We're reducing the wear volume quite considerably. But also the effect of temperature is quite stark. We notice this in a lot of the work that we do, especially above the oxidation temperature of the materials and the coatings. We can significantly reduce wear volumes. So one of the things that I always tell, again, my teams and people that we provide support to, is that we need to understand the oxidation characteristics. We need to understand the trade-off against mechanical properties, and so that we can really optimize the wear rate. And for some materials, for some coatings, we're going to have that sweet spot, and maybe that sweet spot's, say, 500 degrees Celsius. But we need to then work out, compared to the duty cycle of the application, where that sweet spot lies. Is it at the extremes, or is it in the heart of the piece of work that we're doing, the analysis, the testing cycle, and therefore representatives of the real world? As you'll see, when we look at things like the cobalt superalloys, as we know from literature, they are superior in terms of their wear performance. But again, how good is good enough? And how do we provide that appropriate level of wear performance, frictional performance to our customer? I wanted to show you the effect here that we've seen with regard to both the temperature and then the materials rather than the surface treatment. So this combination is a martensitic stainless steel against a cobalt superalloy. And you can see at 600 degrees centigrade, we've got quite a lot of abrasion on the stainless, whereas the cobalt-based superalloy doesn't really look that badly damaged. Indeed, the last phase within that alloy is providing all that wear resistance and is standing proud of the surrounding surface, the surrounding matrix. As we increase the temperature, so here's 850 degrees centigrade, you can see the behavior of those two materials in exactly the same test has changed. So if we start with the cobalt-based superalloy, you can see that the glaze has begun to form. So this is a mixed metal composite where you've got ploughing and you've got mixing of the wear debris into the surface along with oxide, sintering that under pressure and temperature, giving you that really hard sacrificial self-replenishing layer which cobalt-based superalloys are well known for. Whereas the martensitic stainless is again dominated with macro scale abrasion damage, but also it's beginning to see the effects of oxidation at this higher temperature. And when we go to 950 degrees centigrade, really the cobalt-based superalloy that you see at the bottom there is getting into its stride now. It's really beginning to operate effectively at that temperature. Whereas if we look at the stainless steel, you can really see that now there's significant amounts of oxidation, and really we're being dominated by not abrasion anymore, but corrosion or oxidation of that surface, and that's where the volumetric loss from that material is really being derived from. One experience I wanted to kind of show you all today is one I've had over the past few years with regards to design, and I'm very passionate about. We need to incorporate within our tribology work the appropriate use of the principles of tribology, starting with the design of components. And so you can see on the screen at the moment a very small, relatively inert looking thing, and it is what it looks like. It's a simple interference pin. And this pin, what is it, 7 millimeters maybe in length and 5 millimeters in outer diameter. This pin, sole function is to stop something rotating. It is basically an anchor to stop something from moving. And this pin, if it does allow the counterpart to rotate, then the engine system will go into limp home mode. So it's got a critical dependency on the DFMEA, and therefore we need to make sure that this pin does what it needs to do. So to my surprise, maybe 3 or 4 years ago, one of our product engineers came to talk to me and said, Michael, we've got a little bit of a problem. We've got a little bit of a wear on this pin. Can you help us out? And so they started to talk to me a little bit about the problem, what it was, why we were getting this issue in the first place. And we then went through what the requirement was. And they said the requirement for this is 1 million miles. It has to live the full 1 million miles. But unfortunately, at the time, we were only getting the equivalent of about 20,000 miles. So we're way off what we needed. And obviously, this was during the product development cycle. So we're not in production here. We haven't shown this to the customer, etc. But it is important that we work this through and make sure that we've got that solution ready for providing a product to the customer robustly. So we worked really collaboratively. So the material science team, product engineering, the designers, flow control, all different people together with purchasing, etc., came together, and we developed another pin, and it looks like a pin. It's got a different pin, different material, different surface finish, different everything really, a lot more robust. Whereas we've gone from significant abrasive wear now to very, very mild abrasive wear, both empirically and non-empirically modeled. We have the wear data to demonstrate the life of this component. This is used in truck engines that are on the field in the US and in North America right now. And this has a life requirement of 1 million miles like the other pin, but it actually has a real life of 1.5 million miles. So way above what we thought before. So in terms of some other experiences, I wanted to introduce some other things to you, just to kind of give you a flavor for the future in terms of what work's being done in the space from a tribology standpoint. So first I'm going to introduce you to a hydrogen fuel cell air handling device. This is an e-turbocharger, so this provides the air to the fuel cell, and it's also harvesting energy from the exhaust of the fuel cell. And there's some really interesting tribological interfaces in here. So the first is an air bearing system, because we can't poison the fuel cell stack, so we can't use a grease, for example, a hydrocarbon. So we are actively developing the air bearing system here, which has got some really interesting tribological coatings and surfaces. Because we're dealing with humid air, so approximately 95% humid air, and we're expanding that gas through a turbine, we're going to nucleate water as we do so. And because of that, then we're going to have a turbine stage which is erosion resistance. So again, there's really interesting tribological surfaces and coatings that have been developed to solve those problems. And then finally, I think one of the other things I'd say with regards to zero emissions vehicles is the fact that we've got lots of synergies of failing modes now, whereas we didn't have them before. So here, the robust management of synergistic erosion, corrosion, fatigue are really, really important moving forward. The other thing I wanted to talk to you about in terms of zero emissions vehicles is the hydrogen internal combustion engine. So this is classified as a zero emissions vehicle in various different places around the world and seen as a bridge towards the fuel cell in terms of developing the infrastructure for hydrogen adoption. So if you look at the turbo machine here for a typical hydrogen internal combustion engine, really there's two things that we need to be cognizant of from a tribological coatings and surfaces standpoint. The first is optimizing the turbine stage that I mentioned earlier, the variable geometry, the wastegate system, with regards to the fact that we've now got no soot. So it is remarkable when you see the return from a hydrogen internal combustion engine. All the components look like they've just been through a heat cycle. There is no effect of soot. That's really demonstrating the effect that we're having on the environment, which is a real positive. But also it's demonstrating the potential impact from a tribology standpoint, because we no longer have that carbon and soot to lubricate our interfaces. And then finally, we've got to be able to have a bearing system which is tolerant to water and oil. Because we're combusting hydrogen, there's a tendency to have some more water in the oil system, the lubrication system in the engine, and therefore we just need to be able to provide a limit and demonstrate our tolerance to any increases in water content, should there be some. So in terms of some insights from all the work that we've been doing, really what we need to understand are the critical parameters. So we need to have the appropriate mechanical properties at the operating temperature. They need to be optimized for the material pairs. We need the right oxidation resistance, and we need to use that oxide to allow us to grow the tribofilms on the surfaces and use the oxide as sacrificial, self-replenishing. We need there to be a degree of conformability and embeddability in everything that we're using, or else we won't get a robust tribo system with time. We also need a compatibility with new, unique, and different environments. And like I mentioned on my previous slides, we need the ability, the propensity to generate and maintain a very stable glaze on the substrates. And then it really goes without saying, but I will say it anyway, the selection of appropriate tribological combinations is really critical to long-term component durability. So in terms of some future challenges here, just before I wrap up, we've got some key things when we think about surface engineering drivers. So we think around the world at the moment, we've got increasingly stringent emissions regulations. We've got demand for improved product performance and reliability, requirements for a greater product operating range, and then also the ability to utilize cheaper surface treated substrates. So these sometimes are a significant conflict with one another, but we need to work out a path through them, because all of these are placing increased demands on our product, but we need to provide a solution so we can provide that solution to the customer. So in terms of our future challenges, what we really need to be doing here is thinking about how we can make mass production viable surface treatments for net zero product development. We've been doing a lot of that work in this space. I've briefly touched on the previous few slides. We need to keep focusing on this. I think there's some fantastic discussions we've been having already today on this very topic, but we need to put more effort into this field to drive the cost down, for example, and the increase in supply in this area of robust surface treatments. We need the development of some processing technologies to enable reliable and robust surface treatments. Again, I'm talking about the development of products in the hundreds of thousands of ranges every year. So we need to be able to have appropriate processing technologies which are linked very closely to those mass production goals. And then we're always focusing on cost. We want to drive the cost down for the customer and then the consumer at the end of the day. So what we're trying to do there is replace expensive base substrates with surface engineered cost-effective alternatives. On the previous slides, I've talked about cobalt-based superalloys. They are the baseline for a lot of the high temperature tribological work that you would do in this type of environment, but they are very, very expensive. So more we can do with a cheaper alternative, the better. Thanks for listening. Sam, over to you.
Okay, great. Thank you very much, Michael. Fantastic presentation. But great to see this more application-oriented talk, especially with relation to real-life components. Looks like we haven't had any questions in the chat. So I think in terms of time, what I'd like to do is just ask you one quick question, which is when you talked about the redesign and re-optimizing the pin in terms of a tribological analysis, optimization, applying surface engineering techniques, what was the sequence that you went through in order to do this?
Yeah, great question, Sam. So it was very much like what I described on the third slide in this presentation, where go back to first principles, understand what those contact conditions are. If we don't understand those on a piece of paper, let's see if we can model them in CAD and then model them on ANSYS, for example, so we can understand all those contact conditions. And the more information we have about the interface, the more eloquent our solution is going to be. At the end of the day, we don't need it to be really complicated. We have lots of drivers that we can pull, levers we can pull to try and get to that final solution. But it was analysis-led design to begin with that then led us to material selection. Then we did that simple tribology test, go to the component level test, to the system level test, etc. We ran exactly that process, and that's what you get out of it. There are quicker ways of going through it, but sometimes I find if you don't have the correlation loop, and you're not using that correlation loop appropriately, you might find something untoward when you get to the very final step.
Yeah. Absolutely. Thank you very much. Okay, we've got one quick question from BipLab, which we can do now, and then we can move on to our next speaker. So, so they ask, in future, there will be coatings with multifunctional properties. What would they need specifically? I think they're asking about what are the main things you need to optimize for: wear, oxidation resistance, low friction. What do you see the most and are seeing the most?
Yeah, I think if you'd asked me maybe 5 years ago, I would have said wear was the number one. But generally now what we find is a lot of our customers want, obviously, the optimized wear. I wouldn't say low wear. I think that's always a difficult thing because we need to be able to quantify. So optimized levels of wear, but then also an optimized friction response. We need to know what we're getting consistently. So what I like in tribological interfaces is consistent behavior. I don't like peaky behavior, so if we can get something which has maybe a higher friction coefficient but gives us consistent behavior, that's much more attractive than something that's peaky. And then we've got a lot more requirements coming when we think about zero emissions components. So you've got that wear, you've got the friction, but then you've got overlaid on top of that. You've got both the fatigue and the corrosion aspect. So there's so many things that we need to think about, and I think the development of surface treatments is only going to get more complicated in the future, which is great, but we just need to think about that first principle again.
Okay. Thank you very much. Fantastic answer. So I think with that, we'll wrap up your section of the symposium and move on to our final talk. So thank you again very much, Michael, for your talk. We now have Dr. Donald Cohen from Michigan Metrology. I'll bring up your slides in a moment, Donald. There we go.
Okay, ready to go?
Excellent. Take it away.
Okay. Yeah, I appreciate the invite. This should be fun, and I'm glad to be the last one because I get to use some of the information other people have shared with you. You'll see it in my slides as well. So I'm going to talk about the effect of the surface, what I call spatial wavelengths. Sometimes people call them spatial frequencies. Just think in mind that the frequency is 1 over the wavelength, so it's the same idea. But this picture on the bottom right kind of gives you this whole idea. If I said, you know, measure that surface, which is a big surface, you'd have to ask, well, do you want to measure the mountains? Do you want to measure the trees? Or do you want to measure the grass underneath the trees? So when you say, I want to measure the roughness of something, the whole point of my presentation is to help you become aware of the fact that besides just measuring amplitudes on the surface, we need to be concerned about the spatial wavelengths that basically comprise the surface. And in many cases, that may be even more important than the whole amplitude of it. And then I'll discuss how that affects coating a surface and lead to like more or less what's sort of the cutting edge analysis in our field, which is taking on the term called multi-scale analysis. So this mountain here I use as just an example of saying if you were trying to hike this mountain and you have to decide whether you can even hike the mountain, you know, you have to consider, I'll call it surface roughness for now, but we'll call it surface texture, but over different spatial wavelengths. So we might look at, on the left side, the form, the whole shape of that mountain, and maybe those big long lines represent a mile or so, and you might say, okay, it's about a 2 or 3 mile kind of hike. If it was flat, there's some shape to it, so we call that shape you know, form, but the lengths, so the length scale we're measuring is very large, maybe on the order of a mile. If I get on any one particular slope of the mountain, forget the fact that it's kind of tilted and I'm climbing a mountain, so I remove the tilt, I can look at these spatial wavelengths that might be measured on the order of hundreds of yards or something like this. So football fields in the United States anyway, in length. And those kind of length scales tell me something about the terrain I'm going to have to navigate, say, over each major segment of that mountain. And then finally, I might be concerned about what's underneath my feet. In other words, what kind of shoes should I be bringing on this hike? So those spatial wavelengths would be measured the length of 1 foot or less, basically. And that might affect the way I feel friction. It might affect the comfort, how thick my soles have to be, or whatever. So you can see just looking at these 3 domains of spatial wavelength, the form, what we're calling waviness and roughness, affects the function or the questions I'm going to ask. And that turns out to be very relevant in many tribological interfaces as to what spatial wavelengths are critical to the application that you're considering. So if we were to take a standard 2D profilometer and just drag it across the surface, this happens to be some sheet steel, and I'm going to be using this as an example. Think in terms of the steel that's used on the door of a car after it's manufactured, coming right out of the mill, ready to be put into a stamping operation. And that surface has got a lot of interesting texture to it, and you can see it has a long, you know, this is a trace of 15 millimeters, and it has a lot of different spatial wavelengths. It's rich with spatial wavelengths. We have some long spatial wavelengths, and superimposed on those longer sort of spatial wavelengths are shorter ones. So the way we can analyze this is think of it in terms of a spectrum, just like a chemistry spectrum, looking at, you know, wave numbers and all that kind of business. We look at amplitude as a function of spatial wavelength. And so there's some software around, digital metrology is one that has it, that does a nice job of plotting the amplitude as a function of spatial wavelength that makes up the surface. So this actual real profile can be transformed into a Fourier space, if you will, of spatial wavelength versus amplitude. And what you can see here is, like at the 0.5 millimeter wavelength, which is to the middle left of the page, we have a certain amplitude, maybe 0.3 microns. And then within that spectrum, we have a distribution of spatial wavelengths. What goes on in the coating industry in the automotive world of actually painting a car, or called coating a car, is we're always concerned about the final finish. You know, what does it look like when you walk by that car? It's one of the driving factors behind buying a car is how it looks, right? The styling. And it turns out in that industry, there's a sort of standard way of measuring the final painted surface. It uses a machine called a BIC wave scan. And basically it uses optical light scattering, and it does exactly what we've been just talking about. It looks at the way light interacts at the surface, but as a function of spatial wavelengths. So their wavelength range corresponds to the spatial wavelengths on the surface. So there's 5 of these bandwidths that we look at in the paint industry, WA being the shorter wavelengths, 0.1 millimeter to 0.3 millimeters, all the way up to WE, 10 millimeters to 3 millimeters. out of this device, this big wave scan is like a spectrum, just like you'd see with an infrared spectrometer or something else. And what's being plotted is just arbitrary, what we call BIC units, as again, as a function of these spatial wavelengths. And the auto industry goes through a lot of care and trouble to get just the right surface texture of the substrates and all the intermediary kind of processes, and well as the final paint, to get a certain distribution of these BIC units, if you will, as a function of these spatial wavelengths. This happened to be a problem I got involved with a few years back, where steel coming from different suppliers, although meeting the same surface finish requirements, which we'll discuss, once they got painted very differently and looked very differently. So as a result, if it just so happened steel from one supplier was on the front door and steel from another supplier was on the back door, and they were painted at the same time, they wouldn't look the same, even though all the incoming specifications on the raw steel and all the processing after there was the same. So we talk about what we call the worst of the worst surface, that's the wow, and the best of the best surface. So the smaller the BIC numbers, you know, the better in this case we consider the paint to be. Ideally, these should all be the same, so they would paint consistently. And again, the distribution of this is how one relates to the different paint finishes. Here's actually real data. It happened to be kind of ideal data to demonstrate. This was a project that went on for many years. I just grabbed the most, what they used to teach in school, the most typical data, meaning the data that fits your theory the best. But this actually is real data. So this is this was like, say, the front door of a car measured, and this was the rear door of the car measured. But we're measuring it as the specification for the incoming steel. This is the raw substrate, which is using what we call the 0.8 millimeter cutoff. So we're looking at spatial wavelengths of 0.8 millimeters in length and less. And that's kind of a typical way a machine type surface, a metal surface, is measured. That's been in the standard for many, many decades. And so the steel suppliers were very happy. Everyone was meeting print. Everything's going great, except when you painted these surfaces, they didn't paint real well. Notice if you look at the RA measured with this 0.8 millimeter cutoff, these two samples happen to have exactly the same RA. They had different peak count. These parameters are basically the number of peaks per centimeter and so forth. But by being able to look at the spectrum, you can really begin to see that these surfaces, when you look at the full spectrum, look different. But in production, they're not even looking at the profiles. They're just putting a meter on the device and getting an RA number. So the only thing that comes out in production is that number. Both of them are considered good. If we could even look at the profiles, we might have gotten some indication there was a difference. But for sure, if we looked at the spectrums, we would know there's a difference. Here is, in fact, what would have happened if these samples were measured in such a way that we looked at all the different spatial wavelengths. And then, indeed, you'd begin to see that this one that didn't paint well, this is, again, the substrate way before painting, looks quite a bit different than the one that was considered good, even though the RA numbers under the earlier cutoff lengths were the same. If I looked at all these spatial wavelengths, we start to see a little difference in the RA. It's not, dramatically different, and a little bit of difference in the peak count. So what this work realized is, why don't we just set a bandwidth when we measure the incoming substrate around this kind of troubled area? You can see how different this is. What turned out to be painted good, and this turned out to be painted bad. And so we developed a different band, a different spatial bandwidth that we measure and characterize the surface, so we can get a bigger differentiation in RA, as well as in peak count and spacing parameters. But this was nothing more than being able to have the spectrum in front of us, look at a whole series of parts and go, these don't paint well and these paint well. What's different about them? And what was different was their spatial wavelength content. Again, measured at the standard cutoff of 0.8 millimeters, wavelengths of 0.8 millimeters or less, all those parts were considered the same. This brings me to the idea of what could be going on here. This is a concept that's really nicely explained in this book I referenced. So if you want to get into the concept of how fluids flow and form on a surface and a coating and so forth, this book was phenomenal. And this is one slide that basically is trying to summarize a pretty complicated chapter in that book, so bear with me here. But the question here is, if I start to coat a surface, particularly if I'm painting a surface, and ideally maybe I want it to be planar when I'm done, what determines whether that coating is going to conform to the texture or it's going to planarize. And it basically is an interplay between the surface energy of that film, of that fluid, in this case, that's being put on the surface. And the second sort of term, which I'm going to relate to being an energy of interaction of longer term, in the sense that if I started with a raw substrate, nothing on it, and then I started putting film on it, okay, at the very beginning that film touches the surface, I get some kind of interaction. But as the film grows, that interaction has a dependence on the thickness. And so this dependence on the thickness, and it turns out to be the curvature, meaning the second derivative as a function of thickness, which gets into the material properties of the coating film and all that, that interplay between how high the surface energy of the liquid is to air and then the basically long-range interacting forces come together to basically result in how well that surface will planarize. And so what basically happens in our case was you'd have steel that was received, and this was, you know, what ended up being the good one and the bad one, but this is, again, you know, all the wavelengths, so you could clearly see it. And once you coated the steel prior to paint, which is a process we call e-coat, you can see what happens. The e-coat can kind of level and get rid of these what we'll call middle range wavelengths, but the surfaces that had the middle range wavelengths with higher amplitude couldn't be attenuated. The actual e-coat couldn't level that out. So once again, the whole point of my presentation is to just use this as an example of why you should be concerned about the spatial wavelengths of that texture as you begin to understand your tribology interfaces as much as your amplitude, say, and bearing ratio curves. This is what actually is developed now in the industry. There is an industry standard now in this automotive industry here where people who supply steel have to go through a qualification process where we stamp the steel into the shape of a pie pan, measure it. Here's with a Bruker NP Flex. We basically measure two patches, 16 millimeter by 16 millimeter patches, really high magnifications, about 120 images that are all stitched together. Doesn't take too long, about 15, 20 minutes to get each image. And then once we have that image, we're able to, you know, clearly nicely display it. This is what they look like in this bandwidth. So we're looking at a bandwidth of 0.15 millimeters to 2 millimeters. We call this the appearance band. And then once we look at that, in that bandwidth, we can use software that's been available. Digital Metrology also created some really nice software. They were involved in this project, it's called Bandify 3D, which basically takes that whole 3D surface texture, all the spatial wavelengths, which are displayed down here, and then allows you to calculate the actual roughness or other parameters, you know, SA, in different bands. These are chosen to be the bands that are consistent with the paint industry, A, B, C, WA, WB, and so forth. But you can select any bands you need that may be relevant to your application. So this really opened up our eyes, literally, to being able to look at surface roughness, surface texture, again, not just at amplitudes, but look at the spatial wavelengths and to determine which spatial wavelengths might be more relevant to the problem you're going to solve. Also, I want to mention other software now is available as well. Bruker has some really nice software now, Vision 64 Maps, which allows us to do the same thing. We can take this whole three-dimensional image. This is, again, 16 millimeter by 16 millimeter image, millions of data points, and we're doing these incredibly fast Fourier transforms and showing 5 bandwidths, separate bandwidths, all done with Fourier transforms, and what the average roughness is in each of those bandwidths. This is a plot of the spectrum. This is a radial spectral plot at the top left, top center, the radial spectral plot, you know, but same idea of spatial wavelengths there. This feeds right into what we just heard about. That's when I saw the earlier talks, I go, this is perfect, because this is an actual paper I found a few years ago that nicely was showing wear of a cutting tool as a function of a dimensionless parameter, which was the ratio of the coating thickness to basically a parameter related to the roughness, and that's the average radius or curvature of the substrate. Basically, it's kind of like pointing to this picture, which we saw on one of the first slides, in that we seem to show less wear and lower friction if we had some surface texture, and there was a dependence on the coating film thickness as well. And so this is a nice graph. The paper is a really good one to have. That just really systematically went through this. How do I optimize this cutting tool for least amount of wear? And it turned out to be you did want a surface texture with a certain, thickness level. And the question is, how do you produce that surface texture on the film? If you start with the substrate, will it conform, or do you have to go in and roughen it afterwards? But again, a real nice illustration of how the interplay of surface texture and thickness affects tribology and so forth. This leads me to just sort of the last couple slides, and this is sort of the cutting edge now, what's been going on. But way back in the 90s, Chris Brown at Worcester Polytech was really spearheading the development of surface texture measurement beyond RA and looking at, again, I'll say spatial wavelengths here, but in those days we were calling them fractals. And the idea being that if you took a look at a surface texture and you just started tiling it, just kind of, basically measuring the surface area by putting little tiles, triangular tiles on it, adding up the area of all those tiles, well, then the area that you would measure would very much depend upon the scale length that you used to basically cover that surface. And so the idea was, let's look at, say, a parameter like such as surface area. SDR is a measure of surface area as a percentage of increased surface area as a function of these scale lengths. And then maybe we can see how the surface varies as a function of scale length and derive other parameters and so forth. Again, a lot of other software is now starting to do this. I work, as you can tell, with digital metrology as well. And so this is a nice plot from digital metrology showing the actual tiling of a pretty big surface. It's kind of neat. But I wanted to call your attention to this paper, which just came out. This paper came out, was like 2018. To me, that's yesterday. And it was a really huge paper that brought together a lot of people and really introducing the world to what we're calling multi-scale analysis. And it's basically the same concept as what Chris was calling fractals. And this is just an example of the results of that. Again, we now have this in our software where you can, happens to be a pretty nice surface of paper towel, just ordinary paper towel. And what's plotted below this paper towel thing is a graph, and that's this SDR area ratio as a function of scale length. So the scale length of, let's say, 100 microns squared, you can think of it as a 10 by 10 little rectangle, but it's actually triangles that give you that 100 microns squared. And as you see at really small scales, you get a large surface area as you kind of go in and out of all the different features. And as you increase the scale length, this graph just basically rolls down to 1.0, which means the cross-sectional area is the size of, let's say, a 1 millimeter by 1 millimeter flat surface. That'd be 1 square millimeter, and that's it, a perfectly flat mirror. But as you add texture, the surface area increases. And then when you look at the top right display, we're looking at something, this data set just was perfect for this demonstration. The top right display, I set the bandwidth to be from 0.3 millimeters and lower in terms of spatial wavelengths. And as you can see, the SA of this is about 8 microns. The SDR, which is basically a measure of additional surface area, is about 12%. If I now look at just the long spatial wavelengths, which is the bottom plot, you see these nice deep blue areas and high red areas. So these are the mountains, but these mountains are basically ice covered. They're very smooth mountains. As a result, the surface amplitude, the SA, is large. Again, they're mountains, and so the average roughness, SA, is 32 microns. But the overall surface area contributed by these big, tall mountains, again, but they're very smooth, is only about 4%. So this is a classic example of how the spatial wavelengths interplay with what would be considered the average roughness, but you have to be aware of what spatial wavelengths you're looking at, because if you're worried about a fluid wetting this paper towel, it might be those shorter spatial wavelengths that affect the adhesion, and you want to look at those shorter wavelengths, that sort of thing. So to kind of summarize, I wanted to just show a pretty neat little animation. Mike Zucchino does all the marketing and work for my company and some other companies in the surface metrology world. He's been involved in it since the beginning, pretty much. So Sam's going to play this animation, which basically summarizes the whole talk in a nice musical way.
That matter for our application. But what does that really look like? One way to visualize it is to think of sorting different sized stones. The size of the stones is analogous to the size of the surface features. To get just the sizes we care about, we might start by screening out the smallest pebbles and dust. For surface texture, that means filtering out the shortest wavelengths, which may be measurement noise or just small structures that don't impact our application. We call this the short filter, or S filter, or lambda S. We might take this a step further and divide the remaining rocks into larger and smaller sizes. In the surface world, this is like separating roughness from waviness. We call this filter the roughness cutoff, or lambda C, or the L filter. The application determines the size of the filters, and the number of filters as well. For a paint finish, we may need to control several wavelength bands, not just the roughness. There are many ways to visualize surface texture and filtering. To learn more, check out our blog and classes at mitchmet.com.
Okay, and that's it. Any questions?
Thanks, Donald. Okay, great. Fantastic presentation. The surface texture spectroscopy is a really interesting way to take a look at these different these different ways to visualize the length scale and everything with that. Okay, we've got a question from one of our previous speakers, Martin, who asks, in contact mechanics and tribology, often the roughness spectral power density, PSD, is used.
Oh.
Is there a reason you're using amplitude versus wavelength?
Yeah, actually, great question, because, yeah, indeed, all those things are saying the same thing. And the power spectral density is really just related to the amplitude squared and all that. But this is, kudos to my friend Mark Malberg, who wrote that software. It's just that when we're out there explaining to people spatial wavelengths and all that, and in the old days, we were showing power spectral densities to people that aren't familiar with Fourier transforms and all this kind of stuff. When you wrote the software that just nicely showed, look, this is the amplitude of a wavelength as a wavelength, and you can measure a sine wave, and you can show them the amplitude of the sine wave, and you can show them the wavelength, then the light bulb gets off and everyone understands it. This concept of spatial wavelengths, I have to say, is probably one of the most challenging ones in the sort of general surface metrology world. I know a lot of us on this here got a lot of background in Fourier analysis and all that, and spectroscopy, but to a typical person, they've never heard of these concepts, and it can get into a lot of trouble. So that's why it was really a great way to just get the point across to the general people out there.
Okay, thanks. I guess the software is still able to, excuse me, output this, the PSD values as well as the, So very much, just what do you want to get out of your data, really?
Right.
Yeah. Okay. We'll just hang on for a moment or so to see if there's any, one final question. While we're doing that, just like to highlight, for anyone that has not downloaded the attendance certificate that would like this, please go click on the link now. This will not be available after the event. Okay. Okay, I think that's, we haven't had any further questions. So I think with that, Donald will draw your presentation and this symposium to a close. So with that, I'd just like to bring up our closing slides. So just like to say thank you so much to all of our speakers today. Fantastic presentations, great questions from the audience, very engaging talks. Overall, thank you so much to Bruker for the support for us to run this event. As always, we wouldn't be able to run events like this without our partners, and especially big thanks to Bruker for allowing us to run this longer and more complex event. If you want to see more from Surface Ventures, you can check out our website. The link is there. So we've also got our newsletter. If you sign up on the website, you'll get our update emails. We do have a couple of extra events coming up before we close out in December. So please go check out our website and sign up there. And finally, we just like to say, I know some of you have said you'll tag us on LinkedIn. Thank you so much for that. But also please do, if you can, take the time to advertise these lectures to your contacts. And with that, we'd like to say thank you very much and hope you all have a great day. Thank you all. And thanks once again, Donald.
All right. Thank you.
Thank you all. Goodbye.